everyone, and welcome to another session of the Basics to R. This time we're going to go through the analysis of randomized control trials, specifically looking at the practice problem answers that we have for this session. So with that being said, let's go ahead and let's get started. Okay, so first go ahead and open your version of RStudio and just go ahead and I want you to go ahead and load a few things for me. So you can pause your screen if you want. Now, if you've been doing any sort of work already, what I would suggest doing is I would suggest detaching the DPLYR package. The one thing about this package, and I think I've mentioned it before, is while this is great for organizing our data and all sorts of other stuff, it can also become a pain if we don't already have it unloaded, because it can actually mess with some of our code. So we need to make sure that that is at least unattached before we start anything or start using anything. So let's just go ahead and make sure that's attached, and you can see that it's not based on the error in the console. And then we'll just go ahead and we're going to run the pacman command and just load those packages that you see: the readxl, plyr, lme4, car, broom, ggplot2, psych, hmisc, table1, and lsmeans. And just again, we're going to load our data just like we had previously during the walkthrough that I did just in the past video. And this time what we're going to do is we are going to go ahead, same thing, clean up our data a little bit, make it nice and organized, and then categorize our education variable and also the variable for sex. So for all of this, again, we are assuming that we ran a RCT looking at the effects of an intervention on cognitive function, that there are 3 time points for this: baseline, final at 6 months, and then also a 12-month follow-up. So again, the final endpoint is 6 months for this, and then there's a 12-month follow-up period, so that would be 6 months after the end of the intervention. Okay, so what we're going to do next is let's just go ahead and we're going to set up our data for that ANCOVA data set. So if I didn't already include this in the data, we're going to set it up by first creating this time varying data set. So that's going to be where we're going to just take the variables that are time varying. As I mentioned before, those are going to be the variables of ADA's cog, and then also meters walked, or the 6-minute walk test. So we can just check to make sure that that is correct by just going ahead and using the command call names data2, and you can use this down in the console, which will prevent anything from showing up in your workspace. But again, I just look and I go, okay, 1, 2, those are both included, and then 3, 4, 5, 6, 7, 8, 9, so 10 and 11 are my time varying variables. And just as a reminder, we have our data in this long format where it's varying by time according to the time point, time 1, time 2, or time 3. So we're going to go ahead and we're going to only include those variables, the time varying ones in this. It's going to be the same length as data 2, and then we're going to just go ahead and run that command. You will get a warning message. That's okay, nothing to worry about there. Then we're just going to go ahead, we're going to set up a baseline set that's just going to include only the data at baseline that are not time varying. So for this, again, we're just going to use data 2, then set it up in brackets, and then the columns for everything excluding our time varying variables of the ADA's cog and the meters walked. Same thing, length data 2, so same length as data 2. Then we're going to get a comma right here, time equals 1. And now we have a data set of 40 observations from time point 1 with 9 variables. Okay, so next up I'm just going to breeze right through this again. So we're going to set up our data into subsets. So we've got time 1, time 2, time 3, all for the varying variables. So time varying variables at time point 1, time point 2, and then time point 3. We are then going to go ahead and we are going to change the names of these variables just really quickly. So just looking at, for instance, time point 1, we don't have a dot 1 for anything at the end of it. We're going to add a dot 1 to varying dot 1, a dot 2 to varying dot 2, and a dot 3 to varying dot 3. So if we were to look briefly, we now see again that all these variables now have dot 1 at the end of it, and that's just to distinguish that they're from time point 1. Okay, and then now we're going to use the dplyr package to go ahead and create a wide data set where we're going to join the variables by ID across based on time. So now we're going to go ahead and we're going to join everything together, and as you can see, we now have time.1, ADOSCOG.1, wide meters walked.1, and we only have one ID variable, so everything's lining up nice and pretty now. What we're going to do next is we're just going to go ahead, we're going to create this vector called time vars, and all that's going to do is that's going to take the different time variables, so time, time.1, time.2, time.3, and then we are going to go ahead and we're going to just make sure that we remove those time.1, time.2, time.3 variables from our data set, so now it's a little bit prettier. So it's nice and pretty now. No time.1, time.2, time.3 variables in our data set. And then last but not least, because I hate having dot 1 for baseline variables, I'm just going to go ahead and I'm going to change the variables from dot 1 to baseline, and then we're going to get rid of the underscores, so that way it's a very there are no more underscores in the data, so our variable names are a little bit shorter. So if we look again at our data, this is what it looks like. Everything's nice and clean now, and we're ready to do our analyses and answer those questions. So again, this is for the ANCOVA data set. This is not going to be the way we want to set up our data for the mixed linear model. In order to set up our data for the mixed linear model, it's just going to be one line of code. All we're going to have to do is we're just going to go ahead and we're going to enter right here. And again, remember, I'm using the hashtag to identify that this is a note. I'm now creating a new data frame called data3, and this is just going to reshape the wide data that I just made by the ID variable, and I'm going to reshape the wide variable by the time varying data. So just as a reminder, we can count out what those variables are that are time varying. And so if I look here, that is 11, 12, 13, and 14. Time varying in this case are only for variables that are varying at our follow-up time points. Okay, so as a reminder, we are not including time varying variables that are at baseline in terms of this mixed linear model. We are only including in this analysis for a randomized control trial are time varying variables at time points 2, 3, 4, and so on and so forth, but not at baseline. Baseline is being treated as a fixed variable that's not time varying. So again, we can now see that the time varying variables are 11, 12, 13, and 14 right down here, and we have it. We're going to set it up in the long direction, and then it's going to be separated by dot 1 for in terms of the time points. So now we look at our data set, and what does it actually look like? Well, if we look at our wide data first, we can see that we had dot 2, dot 2, dot 3, dot 3. And now if we look at this, we no longer have the dots here, but we now have our time varying data set for time 2 and time 3. So we no longer have time point 1, but we do have time 2 and time 3 in a long format. And this is going to allow us to do our analysis of our mixed linear model analysis for our CT data. Okay, so let's go ahead and let's answer those individual questions. All right, so I'm just going to move this up here just so that way we're all able to see everything. And so question 1. Describe each group at baseline. Are there important group baseline differences which we need to account for in our analysis? Okay, so to do this, there's a number of different ways, as I know you're all familiar with by now, just based on the videos that we've worked through together. But one way that we can do this is we can just go ahead and we can use the table one or the table one package in order to create a list of our different data that at baseline. So in order to do that, first what we would do is we can just create some sort of subset that is only including data at baseline. And so to do that, I would just go ahead and I take my data at whatever my data in whatever format I prefer, and then I can look at it for only our baseline variables of interest. I'm just going to only include the variables that I think are of interest to me. Dput, this command is just going to provide me with a vector that's going to only include the names that I'm interested in. So in this case, I'm just going to use this function right here to call the names of the different variables that are being included from this data frame of baseline. So this data frame of baseline, it's going to have the variables 4 through 6 and then 9 through 11. And we can just go ahead and we can look at that really briefly if we just wanted to call names baseline, and that's going to show me that 2, 3, 4. So I've got 4 through 6 right here. These are going to be included in my table, and then 9, 10, and 11. So 9, 10, 11. So I'm going to have age, sex, education, and then BMI, ADAS, COG, and then meters walked included in my table 1. Okay, so I'm going to run that command really quickly, and then next I'm just going to go ahead and I'm going to use the table 1 package to go ahead and create my table. And you can name this whatever you want, but I'm just going to go ahead and call it table 1 continuous just for clarity. And then I'm just going to use the create table 1 command, call the variables of vars, that's the group of variables that we just named right there, and then I'm going to stratify it by group as we would do for a randomized trial, and then we're going to use the data of baseline that we just created. Okay, and now I'm going to take that table that I just developed, and I'm just going to make sure that it only includes 2 significant digits, just for simplicity, and then we're going to include missing data, so when there are missing data for a variable, and then finally we're going to use quotations just to clarify where things are. Now, if we look, once we run that command, we can see that we have this nice, pretty table. Now, of course, there are going to be some baseline differences that we are looking at in terms of our table 1. So we do have p-values for everything. But as a reminder, baseline differences do not matter. When it comes to a randomized controlled trial, randomization means that differences at baseline are completely and totally random in nature. It's just a matter of chance whether groups are different at baseline. So in this instance, we are not interested in whether there are significant differences between groups at baseline in terms of their outcomes of interest. So yes, there is a significant difference between groups at baseline in terms of meters walked, but that's not something that matters in this instance because we are going to account for baseline differences anyway within our RCT analysis. That would be standard practice for us. If there were differences in another variable, for instance age, it doesn't matter. We are not interested in controlling for age necessarily in our analysis unless we think that age is a variable that's going to influence our results, and we think that age is something that could significantly influence the outcome of interest. So again, we are not testing for baseline differences, and you wouldn't include the p-values for these hypothesis tests within a RCT table 1. Okay, so just make sure that you never, ever really pay attention to baseline differences. These do not matter. Okay, question 2. Moving on to question 2. Using ANCOVA, what are the effects of the intervention on ADAS COG at final? So what covariates should you include and why? Okay, so let's just go ahead and we're going to run a analysis of covariance. So To do that, I'm just going to create this model where, again, I'm using the wide.data frame. So if I look, I have the final time point is cog.2, so that is our final. This was our follow-up time point, so this is the primary endpoint, and then we have our baseline data right here. So to do this, I'm going to go ahead, I'm going to take cog.2, which is our primary endpoint, and I'm going to look at group, since the group is my is going to be the primary independent variable of interest, and then we are going to control for cog at baseline, because that is something that we always have to do within our analysis. Now, depending on what the outcome is, you might be interested in covarying for some other things as well. When it comes to cognition in particular, one thing that there are several things that can influence cognitive function in terms of the effects of an intervention on cognitive function, but three things that are typically included in an analysis would be age, biological sex, and then education as well. Since we know that age, cognitive abilities tend to decline with age, that with education, people with greater educational attainment typically have higher cognitive abilities, and then and then there are obviously sex differences as well in terms of cognitive performance that exist across the lifespan as well. So with that being said, we should probably covary for age, sex, and education. So we're going to include those as covariates within our model of interest. Now, you may have a different opinion on that, and that's okay. I don't profess to have the only opinion or say that there's a right way to covary for it. But again, the one thing that I would stress is that having fewer covariates is going to be of value in terms of your analysis. You should typically try and have the most parsimonious model that you can, and only covary for things that you think will directly influence your outcome of interest and will have directly influenced the effects of the intervention on the outcome of interest. Okay, so this is going to be our model, and then we're going to just go ahead and we can first look at a summary of that model, and we see that there is what appears to be a significant effect of group on the intervention, and then we can go ahead and if we wanted to as well, we can also look at the ANOVA model. Again, there's a significant effect of baseline, but there's not a significant effect of group in the ANOVA. Now, you may be wondering, that doesn't make sense. Why, again, is there no effective group in the ANOVA, but there is an effective group in the summary? And the reason we'll get into in just 1 second. So what we would do next is we would go ahead and we would look at the LS means. So here we're going to just look at group. And we can see that there appear to be some differences here between the intervention and the control in terms of ADAS-Cog score, that the control appears to be have a much lower ADAS-Cog score than the intervention group, indicating that the control has better ADAS-Cog performance at final than the intervention group. But we don't know if that's significant yet. So let's go ahead and let's make let's use LS means to and a contrast statement to determine if indeed there is a difference between groups. So again, we would go ahead and we're going to make that contrast statement that we've used before. We are going to look at treatment versus control. And then we are going to not include any adjustments. And again, you can include adjustments, and adjustments for this would be things like the Tukey adjustment or Bonferroni or whatever it might be. We typically, in this instance, because this is the primary effect, we wouldn't necessarily adjust for anything, but you can if you think that there's something that is going to be of importance to you in terms of adjustment. So we can go ahead and we look at that. And as you can see, again, there is a significant difference between groups when we go ahead and we run our contrast statement. We see that that p-value that we are looking at and the estimate is exactly the same thing as the summary that we got before. So it's the same thing that we're seeing here. Oh, okay, so now that we know what that is, we can go ahead and we can look at the confidence interval for that as well. And to do that, we're just going to go ahead and we can take this statement right here, and then we're just going to add a few other things. We're going to add that parm, just so that way it says that it's a parameter, and then we're going to look at the 95% confidence interval. And so from here, we now see the confidence interval is that there's a difference between 0.4 points and up to 8.5 points between the groups. So what does this mean? Well, it means that the intervention group appears to have gotten significantly worse in cognitive performance following the intervention. So what we clearly have is we have an intervention that's not very good for cognitive function, and we should probably not be doing it. So that's based on what we have for the ANCOVA model. Okay, so now let's go ahead and let's move on to question 3. All right, for question 3, are there missing data when running the ANCOVA? If so, what can we do to impute these missing data? And should we rerun the analysis using imputed data? So the first thing that we can do is we can just go ahead and we can run a description of the data themselves. So we'll use the describe by statement, use y.data, and then we'll look at ADAS-Cog of .2, y.data of group. Let's take a look. And yes, we do see that there are some missing data, that we have one person with missing data from the intervention group and 2 individuals with missing data from the control group. So clearly we didn't include everybody within our analysis. So what we are going to have to do is we're going to have to use some sort of imputation in order to account for those missing data. So to do that, let's go ahead, we're going to create a new data set. We're going to call this y.data2. And again, we're going to use that percent, greater than symbol percent, just to say that this is all for y.data, and then we're going to use the mutate function of Dipler, or dplyr, and we are going to create a variable called ADAS-Cog BCF, or baseline carried forward. And again, you can call this last observation carried forward or baseline carried forward. They mean the same thing here, since there's only one observation time point beforehand. Or you can call it whatever you want. It doesn't really matter, but needless to say, we're going to run baseline carried forward here, just because this is the easiest way that we can do imputation of missing data. And there are other ways, but we're not going over them here today. Okay, so we're then going to use the if-else statement. So in the event that ADAS-Cog 2.2 is missing, then what we are going to do is we are going to use ADAS-Cog at baseline, and then we're going to use, in the event that there are not data missing, we're going to use ADAS-Cog .2. Okay, and we can just go ahead and we'll run that. And now if we look at those data again, and this time using the y.data2, it looks like something did not work there. Oh, that's because I'm using the same variable name. Sorry about that. So now if we use ADAS-Cog BCF.2, we'll notice that we have a complete data set. So we have 20 individuals in each group. Okay, so with that being said, we need to go ahead and we need to run our model again. So this time we're going to run it as model 2, LM, and we're going to go ahead and we're going to call for ADAS-Cog BCF.2 as our independent variable, or as our dependent variable of interest. We're going to go ahead, we're going to include group plus ADAS-Cog at baseline plus age plus sex plus education, and now we're going to use data y.data2, and now we'll just go ahead and we're going to rerun all those commands that we did just a moment ago, but this time we're going to do it with model 2. Okay, so let's go ahead and let's take a look. So it looks like there still is some sort of an effect when we look at when we use this new model where we've imputed missing data with baseline carried forward. And we can see that that there's no group effect when we look at the ANCOVA model, but when we look at the LS means and then we look at the between group difference contrast, we notice that there is indeed a significant difference between groups, ranging between about 0.49 and 0.39 and 8.0 points for the ADAS cog. So what this again represents is that that the intervention group clearly got worse at the final time point in terms of their cognitive performance in comparison to the control. So we should probably not be doing this intervention if we're just looking at using a linear a ANCOVA model. Now, what if we're using a linear mixed model? Well, that's going to be our next question. So, I think actually I skipped ahead a little bit, and this is going to be our answers to question 4. So all that stuff I just went over here in terms of the results of that model, that's the answer to question 4. What are the estimated marginal means for ADAS cog scores for each group in your model? And so for this, sorry about that. So what are the estimated marginal means ADAS cog scores for each group at your final model when you don't use imputed data? So I apologize. That is not the answer. But what is going to be the answer is we're just going to go over really quickly. So to do that, we've already done this already, but we're just going to do it again here. What you're going to do is, again, we're not using the imputed data here. So we're using model 1. So this model right up here, again, I'll just put it right down here for simplicity. And then what we're doing is we're just going to use the LS mean commands for model 1. And then we can look at the contrast for the between group differences. That would be our between group differences in ADAS cog scores. And then we can look at the confidence interval right there. So what we can see is that those are the results for the model. So again, this would be the estimated marginal means and confidence intervals for the imputed outcome. This would be for the unimputed outcome. But regardless of which way we do it, we can notice that when we do the ANCOVA analysis, that there is apparently a significant difference between groups such that the intervention appears to have gotten worse in cognitive performance relative to the control group. Okay, so next up we have question 5. And now we're going to get into the mixed linear model here in just a moment. So using mixed linear modeling, run a random intercept null model. How much variance is accounted for by the intercepts? And now include a random slope, and how much variance is now accounted for? Should we include a random slope as well as an intercept? So if we are doing this model right here, the first thing that we can do is we're just going to go ahead and we're going to create the null model. I'm just going to call this null model, and then I'm going to use Elmer, just like we've done before. And now I'm just going to run using the dependent variable of ADAS cog. And just as a reminder for this is our dependent variable using data set 3 or data 3. And then the null model is only going to include the random intercept term of 1 over one given ID. And then I'm just going to call the data equals 3, or data 3. And now I'm going to summarize that. And from what we can see, it looks as if for this we do have a decent amount of variance in terms of the data. So the variance is accounting for, in these data, we have about 2.336 of the variance in the data for the random effect of ID, and then the residual variance is 54.871. So if we want to look at how much variance is accounted for in the random intercepts model, it would be 2.336 divided by 54.871. and that is about 4%, which is not extremely much, but it is enough such that we can conduct a random effects model. It's worth considering, and it's something that we're going to do in just a second here. Okay, what about if we were trying to make this a random slopes model? Well, as I mentioned before, the way that this would be done is we would just go ahead and we would, instead of having one ID, we're now going to include that time variable instead. So we now have time given ID. Okay, so again, now it's a random effects term where we have time given ID. So let's see what that looks like. And as you can see, just like I mentioned before, it's going to be hard with Elmer to typically run a random effects model wherein we are doing a random slope. It's my opinion that in most instances it doesn't make sense to include a random slope in most randomized control trials unless you have a pretty large and substantial number of individuals and you have a large number of observation points. Otherwise, the random slopes model is probably not going to be your best bet. Using a random intercepts model, however, is something that's going to likely be of use. So I would generally suggest using the random intercepts model rather than a random slopes model. Okay, so now that we know that, let's go ahead and let's move on to question 6. So using linear modeling, what are the estimated marginal mean ADA's COG scores and between group differences at final? Are these results the same or different than your ANCOVA model? Okay, so to do that, we're going to use the same model that we did before, but we're just going to call this model 3. And we're going to use the Elmer term again, so we're going to use the random effects model that we have worked on in the past. So again, ADA's COG is our dependent variable. We're going to have group by time, where we're going to treat time as a fixed categorical variable, thus factor time. And then we are going to use ADA's COG at baseline as a covariate, plus age, plus sex, plus education. And then we're also going to include that one given ID random effects term that we've been using. And again, let's go ahead and we're going to call data 3. Okay, so let's go ahead and we're going to run that. And it looks like there's some issue here right now. Oh, it looks like it's saying that the boundary is singular. So what that might mean is that there's not a whole lot of variance in the data for this particular model, and so there might be an issue in terms of singularity when running this particular model. Now, we're going to still run it anyway, just given what we are working on right now. But if you see this kind of issue, that might mean that you're going to have some problems in terms of being able to detect a result. Okay, so if we look at this, we're still getting estimates for everything, although again, the boundary is singular. That just means that there's an issue with convergence over time, but that's fine for right now. We don't need to worry about it for our model in particular. Okay, now let's look at the LS means as the question asks for. So we're going to first go ahead and we're going to type in LS means for model 3, and then, as you probably can already guess, we're going to look at group, but now we're going to do group by time for our LS mean, and we can see now what the group differences are at time point 2 and then at time point 3. And now we're going to go ahead and we're going to run that contrast statement just like we did before with model 3. Again, group by time, and this time, again, same thing. We're going to do treatment. Oh, excuse me. Treatment versus dot control, and then we're going to adjust for nothing, just like we've done before. Okay, so let's look at the contrast now, and we can see that there, while the intervention group apparently does still have a higher score at final than the control group, it's no longer significant when doing the linear mixed model. Now, the reasons for why this may be could be just based on the fact that we are no longer using data from baseline in terms of our model for the data that are missing, or it may be just based on how the model is being calculated. But as you can see, there is no longer a significant effect of the intervention on cognitive function in either direction, either for or against. And then finally, what we can do is we can go ahead and we can run our contrast statement, and we're just going to run ls means, again, group by time, and again, we're going to run treatment versus control. Not going to adjust for anything again, and then we're going to set the parameters, and the level is equal to 95% confidence interval. And again, we can see what the confidence interval is. It is favoring the fact that the intervention had higher scores on ADAS cog than the control group, but we can see that it's no longer significant. So this is what we can take away from this, is that while yes, indeed, there were from what we can tell is the estimated marginal means for the intervention group are higher than for the control group at final. It looks as if when we do our mixed linear model that there's no longer a significant result. From my estimation, this seems to suggest that this was an issue of power, perhaps when we were using our baseline carry forward approach or our ANCOVA approach, since that approach may have been giving us an effect when in fact there was not an effect. So again, these are practice data, so treat them with caution. But that's it in terms of our practice problems for today. And if you do have any questions, please feel free to email me about any of this. This is the end of our course on randomized control trials. At some point soon, I will have a video that will discuss some of the basics of doing analyses that are longitudinal using observational data. So this will be similar in terms of covering mixed linear models, but instead we'll focus on how we can do that using an observational analysis instead. So thank you for joining, and I look forward to seeing you soon.